everyone. We are very happy to have Pengtao Z here among us today. He is an assistant professor in the ECE department at UC San Diego. Pengtao received his PhD in ML at CMU, and his research interest is in machine learning inspired by human learning and its application to healthcare. So he has been publishing pretty prolifically in the top venues, and he has been recipient of multiple faculty awards. So yeah, we are very happy to have Pengtao. Please go ahead. Thank you.
Thanks, Aria, for the nice introduction. Hello, everyone. It's a great pleasure to share about our recent work on Skillearn, develop machine learning training strategies inspired by humans' learning skills. So in machine learning, eventually we care about the performance, like F1 score, AUC, precision recall, etc. And to achieve good machine learning performance, typically we consider two factors. One is how to design better models. The other is how to collect and annotate more data. So this has been very successful in the general domain. In terms of model designing, for example, to accurately classify images, there has been a sequence of deep neural networks designed with better performance, starting from the AlexNet, then to VGG, ResNet, DeskNet, EfficientNet, etc., and to today's vision transformers. As the capacity and capacity of these models is increasing, the performance is improved significantly. And the same story for data. So in the past decade, there has been many efforts devoted to collecting and annotating more data, starting from CIFAR, then to Caltech, Sun, ImageNet, COCO, etc. As the amount of data becomes larger, and also the annotation becomes richer, we can leverage them to train better models. So this works pretty well in general domains. However, in specialized domains such as healthcare, the story is different. First of all, for model design in the specialized domains such as healthcare, it is difficult to design these models. For one reason is that the domain experts like physicians or medical professionals, they don't have the machine learning background to design models. And for machine learning experts, they don't have the clinical expertise to think about how to design a model that is compatible with the clinical knowledge. So this requires the collaboration between machine learning experts and physicians to design a clinically meaningful model, but the collaboration typically is difficult. And the same thing for data. In healthcare, it is very difficult to collect data because of many administrative issues and policies. Like we have to get the IRB approval, which is a very time-consuming process. And because of many of these privacy and security issues and concerns, typically it is very difficult to get large amounts of data. And even if we get some data, it is very time-consuming and expensive to ask the doctors to label them, such as the segmentation masks or disease regions. Yeah, so in the end, typically we have to work on a small subset, a small set of labeled data. So to address this problem, like which is basically in specialized domains, it is difficult to design better models or collect more data. So we come up with this research question, which is, can we improve machine learning performance without designing new models or collecting more data? So this basically comes to the third pillar of machine learning, which is about the training strategies. Training strategies is basically about, suppose we are given a model and we give some fixed data. How can we think of smarter ways to leverage this small labeled data set and train it on this fixed model to improve the performance. Yeah, so the goal here is basically to develop training strategies to improve machine learning performance without designing new models or collecting more data. To develop these training strategies, we look at how humans learn and try to get some inspirations from there. So let's first make a informal comparison between human learning and machine learning. So in human learning, the factors determining the learning outcome are roughly the following. So it depends on the intelligence of the learner and also the learning materials the learner can access, and also the learning skills of the learner. And these things, so for each of these things, we can find a counterpart in machine learning. So in machine learning, the models are kind of like the intelligence of the learners in human learning. So if we think about the relatively simple linear models such as spot vector machine, then to these nonlinear models like decision tree, and to the up-to-date deep neural networks like transformers, the capacity of these models is increasing. It's kind of like the intelligence, right, of these models is increasing. And then for the learning materials for machine learning, it's basically data. So given a model, it has access to the data, which is kind of like the learning materials in human learning. And the models are going to leverage this data to learn. And then for the last item, the learning skills in human learning, we basically think of that as the training strategies in machine learning. So it's really about how can we develop better ways of utilizing the data and training the model to improve the performance. Yeah, so the training strategies that we are trying to develop are basically inspired by the learning skills in human learning. And so we basically develop a framework called Skillearn that formulates the learning skills in human learning into some training strategies in machine learning, including learning by creating tests, interleaving learning, learning by ignoring, etc. I'm going to talk about 2 instances later on. So here are the basic elements of this Skillearn framework. First of all, in human learning, typically we have a set of learners. For instance, in classroom learning, we have the teacher, we have the teaching assistants, and we have a group of students, and all of them are learners. And analogously, in the Skillearn framework, the learners are basically the models. Right? In a learning framework, we could have multiple models. For example, in the GAN generative adversarial network, the GAN model, there is a generator, there is a discriminator, right? They are basically 2 learners. And in human learning, for each learner, it has multiple aspects to learn. For example, the learner may simultaneously learn how to write, how to draw, how to read, etc. And analogously, in the Skillearn, each model has multiple sets of learnable parameters, including the weight parameters, the architectures, or the weights of the data examples, or the hyperparameters of the optimization algorithms, etc. In human learning, these learners interact with each other, right? For instance, in classroom learning, the teacher learns something, then the teacher teaches this topic to the students, and also the students can mutually teach each other in group discussions. So in the Skillearn framework, we basically use the interaction functions to describe the interaction between models. For instance, in knowledge distillation, we have a teacher model. It trains itself on some training data, then it generates some pseudo labels on unlabeled data. And then these pseudo labels are going to be utilized to train a student model. So this is basically how the teacher and student models interact with each other through an interaction function defined based on the pseudo labels. And this part is basically trying to mimic the interaction between learners in human learning. And in human learning, typically the learning is organized into multiple learning stages. For instance, in classroom learning, the teacher first need to learn something to get prepared for the lecture. Then during the lecture, the teacher illustrate this topic to the students, and the students learn that topic, and later on, the students are going to do the homework and take tests, etc., to enhance the learning outcome. So there are multiple stages here. And similarly, in Skillearn, we basically organize the learning into multiple learning stages, such as a teacher model can train itself, then it performs knowledge distillation to a student model, then we can evaluate the student model, etc. So there are multiple stages here. And in human learning, one important learning tool is to use tests to improve the learning outcome. And similarly, in Skillearn, we have this key step, which is validation, to validate the learning outcomes of the different models and use the validation performance to drive the learning. And then finally, in human learning, the learners have access to the learning materials, right? And in Skillearn, that's basically the data. It could be training data, validation data, unlabeled data, and some auxiliary data, etc. Yeah, so these are basically the elements in the Skillearn framework, which contains models, interactions between models, and the models have multiple sets of learnable parameters, and the learning is organized into multiple learning stages, including a validation stage, and the learning is conducted on different sources of data. So this is a general formulation of the Skillearn framework. It is based on multi-level optimization. So in multi-level optimization, there are multiple optimization problems, like this is problem 1, 2, K, etc. And these different optimization problems are nested with each other. For example, the output of the first optimization problem, which is basically the optimal solution after solving the first optimization problem, will be utilized as input to the second optimization problem. So this guy here, W1 star, which is the optimal solution of the first problem, is going to be utilized to define the objective function in the second optimization problem. And similarly, the output of the second optimization problem is going to be the input of the third one, and so on for the following stages as well. So we utilize this multi-level optimization framework to emulate the different learning stages in Skillearn. Right? So we have multiple learning stages, and for each learning stage, we use an optimization problem to describe that stage. And these different stages are nested with each other because we want to learn all these different stages end to end. Not only the earlier stages have influence over the later stages, but also the later stages can provide some feedback to the earlier stages. Yeah, so we want to put them into a holistic framework to enable all these different stages to be conducted end to end to achieve the overall best performance. So at each stage, we have so a subset of the learners, these learner models, are going to participate in the learning. And we have some data for this subset of learners. And these learners also have some, so for this subset of learners, they have the learnable parameters. And some of these parameters are going to be learned at this stage. And other learnable parameters are not going to be updated at these states, but rather they are going to be learned at a later stage. Yeah, so here W1 means the parameters that is going to be learned at this stage, which has optimization variables here. And U1 are some other learnable parameters which are tentatively fixed at this stage and are going to be updated later on, such as in this final validation stage. Then we have some data, and we can define a training loss to train these learnable parameters W1. And we also have these interaction functions I to basically describe how this subset of learners interact with each other at this stage. And similarly, we define other learning stages as well, including training losses and interaction functions, etc. And the output of each stage is going to be utilized as the input of our future stage. So this is a quick introduction about this general framework, including these elements and this general formulation. So here are some a quick summary about what we have done so far in this project. So the Skillearn framework is what I just described. It is a general programming framework that enables users to quickly develop machine learning training strategies inspired by humans' learning skills. And this framework is based on multi-level optimization. To make the programming of multi-level optimization easier, we built a framework called Betty. It is a programming framework for multi-level optimization. Basically, in this framework, all you need to do is to utilize the interface to define this multi-level optimization problem, including what stages it has for each stage, what is the optimization problem, and what is the dependency between the different stages. That is on the front end of this framework. Then in the back end, this framework can automatically use different optimization algorithms to solve this multi-level optimization problem. But from a user perspective, the user does not need to know how the backend works. All the user need to do is to specify the problem in the front end, and the system is going to automatically handle the optimization in the backend. Yeah, so this system is a support for this general Skillearn framework. Then on top of the Skillearn framework, we basically develop different instances. So here are some of these example instances. So for each instance, such as learning by self-explanation, we basically take a human learning skill from the behavioral science literature, cognitive science literature, or educational science, etc. For example, it could be learning by self-explanation, which is a human learning skill. Then we understand how it works for human, and basically understand what are the elements of that learning skill, including what would be the learners, how they interact, what they learn, what are the learning stages, etc. Then we leverage the Skillearn framework to map those elements in learning by self-explanation into these mathematical objects. And then we instantiate this general formulation into a specific multi-level optimization-based formulation for this particular human learning skill. And in the end, we get a training strategy called learning by self-explanation. Yeah, so all these instances are basically work like that. Then given this, so these guys are training strategies, they can be utilized to improve different machine learning tasks, such as neural architecture search or data reweighting, data generation, etc. Yeah, so we mostly focus on neural architecture search and data reweighting. And given these improved machine learning tasks, we apply them to solve some significant healthcare applications, such as detecting pneumonia from chest X-rays, etc. Then for the next step, I'm going to talk about two particular instances of the Skillearn framework to illustrate how it works. The first one is learning by parsing tests. So learning by parsing tests is a very important learning strategy in human learning. Right? As students, we can improve our learning outcome by taking these tests. And as teachers, we can also learn how to create tests to help the students improve the learning outcome. Basically, it works as follows. We have a learner, which is a student, and we also have a tester, which is a teacher. And the teacher has access to a test bank, basically contains different kinds of questions that can be put together into exams. So the learner learns something, and the teacher then is going to create a test to test the learner. And in the test, the learner, of course, is going to make mistakes. And the learner then look at those mistakes and identify the weakness in its previous learning. And then it elaborates this identified weakness to improve the learning outcome, basically relearn the topic and try to address those weaknesses. And then after doing that, the learner's learning capability is improved because it can understand and address the weakness identified in the previous test. And then the tester is going to create a more difficult test to further test the learner. And the learner is going to take it and identify some further weakness and relearn the topic to address those further weakness. And this process basically repeats. Yeah, so from the tester's perspective, it will create a sequence of tests with increasing difficulty. And the learner are going to try to improve its learning outcome so that it can pass this sequence of tests, which are increasingly difficult. Yeah, so this is basically how humans learn using tests. And we try to use the Skillearn framework to emulate this process and develop a machine learning training strategy called learning by parsing tests. Yeah, so in this machine learning training strategy, we have two learner models. The first one is a learner. The second one is a tester. And for the learner, it will try to train a sequence of models which are increasingly powerful. So basically, model M2 is better than M1, and model M3 is better than M2. And from on the tester side, it will create a sequence of tests, T1, T2, T3, etc., which are more and more difficult. So basically, T2 is more difficult than T1, and T3 is more difficult than T2. And here is how these two learners interact. And the interaction is basically based on the errors that the learner makes in this test. So the learner starts with a model M1, and the tester is going to create a test T1 to evaluate M1, to basically validate how powerful M1 is. And that evaluation error is denoted by R1. So this is the first step. Then let's first look at the tester. The tester observes R1, which is the error of M1 on T1. And now the tester basically wants to create a new test T2 so that the error of M1 on T2 is going to be increased. So the error of M1 on T2 is R2, and R2 is expected to be larger than R1. Yeah, T2 here is basically something that is that can be optimized. The tester create a new test T2 by solving an optimization problem so that R2 is larger than R1. Now let's look at the learner. So the learner observe R2 and T2. And from the learner's perspective, it basically wants to train a new model, M2, so that the performance of M2 on T2 is better. Basically, the error R3, which is the error of M2 on T2, is going to be smaller than R2. Yeah, so the learner basically wants to train a better model to reduce this error. And this process repeats until convergence. So mathematically, this is basically solving a min-max problem. Right? So for the so here L so C here is a test created by the tester, and A here is the model of the learner, and LAC is basically the performance, the loss of the learner A on the test C created by the tester. And for the tester, it basically wants to create a test C to increase this loss, to make the learner behave worse on the test. And for the learner, it will try to improve its model A so that this loss is minimized. So basically, no matter how difficult a test C is created, the learner wants to improve its model to minimize the loss on that test. Now let's see how can we instantiate the general scalar framework to this particular learning strategy called learning by parsing test, LPT. We can do a side-by-side comparison. So in learner, the first elements are the learners. And in the LPT, we have two learners. One is a student learner. The other is the tester. The tester creates tests, and the learner try to leverage those tests to improve itself. And the second element in scalar are the learnable parameters for each learner. And then now let's see in LPT, for the student learner, there are two sets of learnable parameters. One is the weight parameters of this neural network, and the second one is the neural architecture is also learnable. Then for the tester, it has a data encoder, has a test creator. So the data encoder basically take a data example as input and learn embedding, and that embedding is going to be fed into a test creator to determine whether this example should be selected as a test question. And it also has some targeted task executor. Yeah, so it has basically three sets of learnable parameters. Then in scalar, the other element is basically the interaction function, describing how these different learners interact with each other. And in LPT, that interaction function is basically the learner's validation loss on a test created by the tester. Yeah, so basically this one. So the validation loss of the learner A on the test C created by the tester. And this tester and learner interact by solving a min-max problem with respect to this loss function here. Then for the learning stages in scalar, another element in scalar are basically the learning stages. And in LPT, we have three learning stages. In the first stage, the learner trains its network weights with its architecture tentatively fixed. And in the second stage, the tester trains its data encoder and the targeted task executor. And in the third stage, the learner updates its architecture by minimizing this validation loss. And the tester updates its test creator by maximizing this validation loss. Yeah, so we have three stages here. And in each stage, a subset of learners are involved. For example, in stage one, this subset contains only the student learner. And in stage two, the subset contains only the tester. And in the third stage, both the learner and the tester are involved. At each stage, we learn some parameters and with other parameters fixed. So for the learner, in the first stage, it learns the weight parameters of the neural network, and the architecture of the network is tentatively fixed. And similarly for other stages. For the data sets in this learning by parsing test, we have the training data, and we also have this test bank, which is basically a large validation set. So in the Skillearn framework, it is generally formulated as a multi-level optimization problem. And so here, for the, yeah, sorry, give me a second. So here for this learning by parsing test, we basically instantiate that general multi-level optimization problem into a specific multi-level optimization framework, which contains 3 levels. At the first level, we train the weight parameters W of the learner by minimizing training loss defined on some training data set D. And A, which is the architecture of the learner, is tentatively fixed. So we solve this optimization problem, and we get the optimal weight parameters W star, which is a function of A, because A is not learned yet. It is a free variable. So W star is basically a function of A. And this optimization problem basically corresponds to this first learning stage, right, where the learner trains its network weights. And then in the second stage, we have another optimization problem to basically emulate this behavior, where the tester trains data encoder and the target task executor. Right, this is the behavior in this stage 2, and we define this optimization problem here to emulate that. Then in the third stage, we basically solve this min-max problem, where the learner try to minimize this loss by updating the architecture A, and the tester try to create a test C to maximize the learner's validation loss. And you can see that, so A, the architecture of the learner, which is tentatively fixed in the first stage, is updated in the third stage. And all these different stages are nested. So basically, they are conducted end to end. So for instance, every time after we solve this, the problem in the third stage, we are going to get a new architecture A. Then this architecture A is going to be changed, and this loss function is going to be different, and we need to redo the first stage and get a new W star. And after we get a new W star, then this loss function here is changed accordingly, and we need to solve this optimization problem again. And so this process iterates, and all these different stages are mutually influencing each other, and they are conducted end to end to achieve the overall best performance. Here are some results. We applied for neural architecture search, NAS. So these are the results on CFAR 100, C100, and the CFAR 10, C10. So these are the classification errors on the test set. We can see that the first message is, so our framework denoted by LPPDT, it is a learning strategy. It's not a new deep neural network. So the learning strategy can be applied to improve different neural architecture search methods. Right? So in the baselines, in the literature, we have different NAS methods, such as darts, PC darts, P darts, PR darts, etc. And our framework is a general training strategy that can be applied to improve different NAS methods. So we apply it to these different baselines. And we can see that applying our framework to this baseline NAS methods, we achieve significantly better performance in all these different scenario cases. And here are some state-of-the-art baselines in the NAS literature, and our method outperform these state-of-the-art baselines. So because in this learning by parsing test learning strategy, the one primary goal is we want the learner to be able to solve any difficult tests created by the tester. So that basically means if successful, the learner trained by this framework should be able to handle difficult test data. Yeah, to verify this, we basically ask human annotators to select 200 hard examples from the test data, which these human annotators think are difficult to recognize. And we can see that on this 200 hard example set, our method achieves much better performance than the baselines without utilizing our framework. And so this basically demonstrates that by utilizing this learning by parsing test training strategy, we can search for neural architectures that are able to deal with difficult test cases. And in this figure, we basically show some tests created at different epochs. So each test is basically a selected subset of validation examples. And from the design of this framework, the tester is expected to create tests that are more and more difficult. So from this figure, we can see that for this tiger class, in epoch 0, it basically creates a test which is relatively easy. We can immediately see these are tiger images. And as the training epoch increases, we can see that these selected tests are more and more difficult to solve, right? So for example, for these images here, it's kind of difficult to recognize this is a tiger. So this is actually the face of a tiger. We need to look at it very carefully to identify this is a tiger. So this is much harder than these guys. So this basically shows that the tester in our framework is indeed able to create tests that are increasingly difficult. Here are some results on ImageNet. Again, we show that by applying our general training strategy to different NAS methods, we can achieve better performance. Yeah, these are the classification errors. Okay, so this is about the first instance, learning by parsing tests, where we utilize this general framework Skillearn to formulate this human learning skill into a machine learning training strategy. Next, I'm going to quickly give an overview about another instance. So in human learning, there is a learning technique called interleaving learning. Basically, it works as follows. Suppose the human learner has 3 tasks, 1, 2, 3. And the traditional block learning is basically we first solve class 1, then after 1 is finished, we move to class 2, task 2, and after 2 is finished, we move to task 3. So for each task, it is solved completely before we move to the next task. Interleaving learning is basically like this. So we work on task 1 for a short period, then we quickly move to task 2, and then we quickly move to task 3. Then after we work on task 3 for a while, we get back to task 1 and repeat this process. Right? So 1, 2, 3, 1, 2, 3. So for each task, we only work on it for a short while, and then we quickly move to the next task. And later we will revisit the first task and repeat this process. So this is called interleaving learning. There are some psychology and education literature showing that interleaving learning can be more effective than block learning in many learning tasks. So we basically want to take this interleaving learning technique from human and use the Skillearn framework to formulate it into a machine learning training strategy. Yeah, so basically in our machine learning framework, we have key tasks, and each task is denoted by LK. And we perform these key tasks in M rounds. So basically, we have M rounds of interleaving learning. So in each round, we learn a task, then quickly move to the next one, then the next one, etc. And after we worked on all the tasks, including L1 to LK, then we move to the second round. So between round 1 and round 2, we move from LK to L1. So we basically get back to L1 and redo this learning. And then we move to round 3, etc. And do this interleaving learning for M rounds. Between two tasks, say task L and L minus 1, we basically transfer knowledge between the learners. So for task L, we have a learner WL, and for task L minus 1, we have a learner WL minus 1. And L minus 1, after we learn it, we get some optimal weights for that learner, denoted by W tilde. And we are going to use these optimal weights to regularize the learning of WL. And so this simple regularization function basically encourages the knowledge transfer from task L minus 1 to task L. And because all these different tasks are organized into a loop, and then we can basically transfer knowledge from any task to any other task along the loop. So again, to leverage Skillearn to develop this interleaving learning technique, we basically instantiate the elements in Skillearn to the specific objects in interleaving learning. So for learners in interleaving learning, we have the key learners, right? Each learner is in charge of one task. And for the learnable parameters, all these learners have a shared learnable architecture of the encoder. And for the weight parameters of the encoders in different learners, they are different. So WKM basically denotes the encoder weights of learner K in round M, and HKM denotes the head of each learner in each round. So the head is task specific. For example, if we solve an object detection problem, then this head could be a cascaded RCNN head for object detection. Then for the interaction between the learners, we use this simple L2 regularizer. Basically, we encourage the weight parameters of learner L to be close to the weight parameters of the previous learner L minus 1 to transfer the knowledge between the two learners. Then for the learning stages, we have K times M stages in total, where M is the total number of rounds, and K is the total number of learners. In the first stage, learner 1 trains its encoder weights and head in round 1. And in a middle stage, the learner K trains encoder weights and head in round M, and by leveraging the knowledge from learner K minus 1. And in the final stage, we update the architecture of the encoder. We can instantiate the general multi-level optimization-based framework in Skillearn into this particular multi-level optimization formulation for interleaving learning. Basically, at each stage, we train a particular learner, which is learner K in round M. And when we train this learner, we leverage the knowledge from the previous learner. And these different stages are organized into M rounds to mimic the interleaving behavior. So this is also applied for neural architecture search. So again, our framework denoted by IMTL, it is a general training strategy that can be applied to improve different neural architecture search methods. And these results on CIFAR 10, CIFAR 100, and ImageNet, as we can see, applying this interleaving learning method to this different NAS baselines, we can achieve significantly lower test errors. And we also compared with the vanilla multitask learning neural architecture search methods, which basically put together all these loss functions of different tasks into a single objective and minimize that without considering interleaving learning. We can see that our method outperforms this multitask learning baselines, which demonstrates the benefits of interleaving learning. To conclude, so basically we want to improve machine learning performance. However, in specialized domains such as healthcare, it is not easy to design better models, and it is very difficult to collect more data. So we approach this problem from a different perspective, basically develop better training strategies to train better models given a fixed set of data. And to develop these training strategies, we try to get inspirations from human learning. We basically look at what are effective learning techniques in human learning, and we develop this general scalar framework to formulate those human learning techniques into machine learning training strategies. And on different instances and different tasks, we demonstrate that by developing these human-inspired training strategies, we can achieve better machine learning performance without designing new models or collecting more data. With that, I like to conclude here, and thank you for your attention. Thanks.
Thank you very much, Pengtao. It was a really nice talk. So is there any question for Pengtao from the audience?
Yeah, and this is Ismail Bustani. I have a question. Can you hear me?
Yes.
Yeah, thank you, Professor Z. This is a great talk. Very, very insightful. So I have a question. If you have a question answering task in the medical realm, which is quite often, the examples you showed us for the tester to generate new tests were for images, so you can blur images and modify them. How would you do that for an answer? How would you generate answers by the tester in that context for question answering?
Yeah. So for so we have a relevant. We have another instance we developed called peer questioning. Yeah. So in that training strategy, we basically applied for visual question answering on pathology images. So there, for the tester, it basically have two models. The first one is to generate an image. The second model is a conditional generator, which takes an image as input and then generates the question together with the answer. And these two models are basically trained using the training data in this VQA data set.
Okay, that's great. I mean, I understand for the radiology questions, but let's say I have a maybe it's a diagnostic that doesn't have a radiology image attached to it. The patient will give some questions, some answers, textual answers. How would your Skillearn can be applied for textual input, not just image? I mean, I'm sure it does, but how would you handle that if it's not images, if it's textual information? How would you how would
Yeah.
you test there?
Yeah, so basically for the the framework here we develop is basically a general framework that try to mimic the learning technique in human learning. And regarding the specific applications and models, so the framework is agnostic to that. So basically we can use any differentiable models and plug them into the framework. Suppose we want to work on texts, then we basically replace these data encoders and also these text creators with some models in NLP, such as GPT or BART, etc.
Got it. Thank you. Thank you.
Thanks.
Great.
Any other question? If not, then let's thank Pengtao again. It was a really enlightening talk, and we were very happy to have you here.
Thank you, everyone.
Thank you.
Thank you, Arya. Yeah.
Thanks.
Thank you. Bye-bye.
Goodbye.